Today's lesson is on triangles and quadrilaterals, and what we will discuss today is the triangle angle theorem. First, I'm going to show you how to deduce it yourself, then we're going to define exactly what that is, and then we're going to do our first ever proof of geometry, and we're going to prove it. And then finally, we'll talk about how to use the triangle angle theorem. Then we're going to classify triangles, and we'll learn that triangles can be classified by either angle or by side. And finally, we will classify different types of quadrilaterals. So first, let's talk about the triangle angle theorem. So to deduce the triangle angle theorem, if you take a piece of paper and cut it into a triangle, then if you take the angles of the triangle and tear them off as shown. So I'm going to take that triangle, I'm going to number them, and then I'm just going to rip off the 3 different corners of the triangle. You can pause the video and do that. Now take the 3 angles and put them adjacent to each other as shown. So like that. And again, I'll let you take a second and pause the video to do that. Now you can answer this question: what kind of angle is formed by those 3 smaller angles? And therefore, what is that angle's measure? And hopefully when you look at that, you can see that it is a straight angle, and so therefore the angle's measure is 180 degrees. And then you can make a conjecture about the sum of the measures of the angles of a triangle. And you could make a conjecture that the angles of a triangle, of any triangle, always add up to 180 degrees. And you would be correct, as we will see right here. The definition of the triangle angle theorem is that the sum of the measures of the angles of a triangle is 180 degrees. So if I have a triangle ABC, then I know that the measure of angle A plus the measure of angle B plus the measure of angle C, put all that together, and that equals 180 degrees. And that's the case for any triangle. Now let's take a minute and try to prove it. Now, I'm not going to expect you to be able to prove it yet, but this is the kind of thing we will do in later units of geometry, and this is the part of geometry that's the most fun. So, how do I prove that? So again, let's start out with a triangle, and I'm going to label it ABC, or I could just as easily label it with angle 1, angle 2, and angle 3. So the first step is I'm going to draw a line L through point C that is parallel to line AB. So there's that line right there. I just drew that line in there. And secondly, I'll note that angle 1 is equal to, or the measures are equal, they are congruent angles, to angle 1 prime. And why is that? And the answer is because they are alternate interior angles. They're on alternate sides of the transversal, inside or on the interior of the parallel lines. So therefore they are congruent angles. Now, note the same thing is true for angle 2 and angle 2 prime. Again, why? Because they are alternate interior angles on alternate sides, opposite sides of the transversal, on the inside of the parallel lines. So now I can note that angle 1 prime, angle 3, and angle 2 prime together form a straight line, sort of like they did for the paper that you ripped up. And straight lines have 180 degrees in them. Therefore, I know that if 1 prime plus 3 plus 2 prime equals 180, and I know that 1 equals 1 prime and 2 equals 2 prime, then I can conclude that angle 1 plus angle 3 plus angle 2 equals 180. And that proves the triangle angle theorem. Now that was sort of an informal proof. Now let's do a more formal proof, which is called a 2-column proof, and we'll do these in a future unit. I just want to expose them to you right now. All 2-column proofs start with a statement, and every statement has a reason that goes along with it. So the first statement I'll do for the first point we did up there. So I'm going to draw a line through C. And so the statement just says create line L, and there it is, that is such that it is parallel to line AB. Okay, so it's essentially just the same thing we said, but now I need a reason. And the reason is that through any given point, there exists only one line that is parallel to another line. So there's only one of these lines. If there were multiple lines and I said create one, then you wouldn't know which one I was creating. But this is saying there's only one. Line L can only be in one place, and that's where we have it. Okay? The next statement is just going to be number 2 above, which just says that angle 1 is congruent to angle 1 prime, and we know the reason why. That's because alternate interior angles are congruent. The same thing is true with our next statement, which is just going to be 2 is congruent to 2 prime because alternate interior angles are congruent. Next statement, again, is just going to be like 4 above, which is that the measure of angle 1 prime plus the measure of angle 3 plus the measure of angle 2 prime equals 80 degrees. Sorry, 180 degrees. And that is because of the angle addition postulate, or you could just say that an angle is equal to the sum of its parts. And so that straight angle there is made up of angle 1 prime and angle 3 and angle 2. So if they all equal 180, then it equals 180. And then finally, the thing we're trying to actually prove is the fifth one, which is that measure of angle 1 plus the measure of angle 3 plus the measure of angle 2 equals 180. And the reason is substitution. I can sub in 1 prime for 1 and 2 prime for 2. So that is our first exposure to the proof of two-column proof. Now I'd like to talk about how to use the triangle angle theorem. So there's a triangle, and it's asking me to determine what is the measure of that final angle. So what I know from the triangle angle theorem is that the sum of the angles is 180 degrees. So 70 plus 45 plus x, I'll just call that question mark x, equals 180. Combine my like terms, and I have 115 plus x equals 180. Subtract 115 from both sides, and I end up with x equals 65. We can do the same thing if instead of a variable we have a variable and an expression. So again, it's the same thing. All the angles add up to 180. So 45 plus x plus 52, that other angle, plus 90, because that one with the 90 degree sign and the right angle sign is 90 degrees, equals 180. Combine like terms, 187 plus x equals 180. Subtract 187 from both sides, and I end up with x equals -7. Finally, let's talk about how to categorize triangles. And triangles are categorized either by angle. If all the angles are congruent, then it's called an equiangular triangle. If if all the angles are acute, then it's called an acute triangle. If one of the angles is right, then it's a right triangle. And if one of the angles is obtuse, it's an obtuse triangle. And since we know that from the triangle angle theorem that a triangle may only have 180 degrees, we know that no triangle could have 2 right angles, because that would be all 180 degrees right there, and there'd be nothing left for the third angle. And no triangle can have 2 obtuse angles, because that's angles over 90 degrees, and you only have 180 to play with in a triangle. So if you have 2 over 90, there'd be nothing left, or you have a negative angle for the third. So a right triangle can only have 1 right angle, and an obtuse triangle can only have 1 obtuse angle. So we can categorize by angle, or we can categorize by side. If all 3 sides are equal, it's called an equilateral. If 2 sides are equal, then it's called an isosceles. And if no sides are congruent, then it's called a scalene triangle. Now, one thing that you will quickly note in geometry is that these two things are actually the same. If the measure of the 3 sides are equal, then the measure of the 3 angles are equal. And so every equilateral triangle is also an equiangular, and every equiangular is also an equilateral. So it just gets confusing. So in geometry, we don't use this term equiangular. It's true, but we tend not to use it. Instead, we use the term equilateral. So if I ask you what kind of triangle it is, and I ask you to say determine by angle, and you call it equilateral, which technically is something by side, I would say that that is correct and fine. Right. And finally, we can categorize triangles by both angle and side. So for example, an acute triangle could be an acute scalene or an acute isosceles. A right triangle could be a right scalene or a right isosceles. And an obtuse triangle could be an obtuse scalene or an obtuse isosceles. But there's only one kind of equilateral. An equilateral is an equilateral, that's it. The final thing I want to do is talk about special types of quadrilaterals and how to define them. So the first is a parallelogram. That is a quadrilateral with both pairs of opposite sides parallel. And you can see that in the diagram there, that the opposite sides are parallel to each other. A rhombus is a parallelogram, but it's a special kind of parallelogram that all four sides are the same length. All four sides are congruent. A rectangle is a parallelogram with four right angles. So again, the sides are parallel, but the angles are all right angles. And a square is a combination of those. It's a parallelogram with four congruent sides and four right angles. So a square is really a rhombus and a rectangle and a parallelogram, all of them. A kite is a quadrilateral with the two pairs of adjacent sides congruent and no opposite sides congruent. So you can see there in that diagram, the two sides on the left are both the same size, and the two sides on the right are the same size, but they're different from each other. And finally, a trapezoid is a quadrilateral with one pair of parallel sides, and you can see that in the diagram. And there's a special kind of trapezoid called an isosceles trapezoid that is a trapezoid that has its non-parallel sides are the same size, and you can see that in the diagram over there. Now, one way of thinking about special quadrilaterals, trying to remember all of these definitions may be difficult, so I find it easier, I think, to do it this way. So start with just quadrilaterals. So there's a regular old quadrilateral. It's got no parallel sides, nothing equal. It's just a quadrilateral, nothing special about it at all. And the first branch that we can branch off is say, well, what if there are no pairs of parallel sides? Then we only have one special type of quadrilateral. Again, there are a million types of a million different quadrilaterals that aren't special, and right there is one of them. But a special type of quadrilateral is a kite if it has no pairs of parallel sides. And again, a kite is if the two pairs of adjacent sides are congruent. And you can see that in the diagram. The next sort of branch of our quadrilateral is if we have one pair of parallel sides. And that's where we get to a trapezoid, and a specific type of trapezoid is called an isosceles trapezoid. And the final branch of our quadrilateral tree is if I have two pairs of parallel sides, and that again is a parallelogram. And if that parallelogram has right angles, then it's called a rectangle. If that parallelogram has congruent sides, then it's called a rhombus. And if it has both right angles and congruent sides, so both those things are true, then it's called a square. So there's a visual way of being able to see the different branches of the trees of the special types of quadrilaterals.